You know, it's pretty wild when you stop and think about it. The warmth you feel from the sun, the signal that lets you watch this on your phone, even the X-rays a doctor uses, what could they possibly have in common? Well, today we're going to unravel that puzzle. It turns out they're all part of a single incredible concept, a kind of hidden, invisible rainbow that's everywhere. And the story of how we discovered it, it's one of the greatest scientific detective stories of all time.
So here's how we're going to break it down. We'll start with this puzzle in our everyday lives, then dive into a 19th century mystery. We'll see how a single idea led to an incredible prediction, how that was proven, and finally how it unlocked this invisible rainbow that basically powers our whole world.
All right, let's dive right in. Section 1. A world of waves. We're surrounded by all these forces and gadgets that, on the surface, seem to have absolutely nothing to do with each other. Okay, so here it is. What on earth do the heat from the sun, your phone's signal, a microwave oven, and a medical X-ray all have in common? Think about it. The sun's warmth travels through the vacuum of space. Your phone magically pulls a signal out of thin air. An X-ray sees right through you. They just don't seem connected at all. But they are. They're all the exact same thing, just in a different disguise. They're a very special kind of wave. So to understand this, we need a quick primer on waves. They basically come in two main flavors. You've got longitudinal waves. Think of a slinky. You push from one end, the compression travels along the slinky. That's how sound works. But the one we care about, the key to this whole mystery, is the transverse wave. This is more like shaking a rope up and down. The wave moves forward, but the rope itself moves perpendicular to that direction. You know, like ripples on a pond. And that right there, that's our hero.
And this is what those things from our first question really are. The heat, the signals, the X-rays, they're all electromagnetic waves. They are transverse waves, but instead of water wiggling up and down, it's an electric field and a magnetic field doing this intricate little dance. They oscillate, always perpendicular to each other and to the direction the wave is going. It's wild. Each field creates the other, over and over, as they fly through space. But seriously, how could anyone possibly figure that out just from thinking about it?
Well, to answer that, we've got to go back in time. This brings us to our next section, Maxwell's missing piece. We're heading to the 19th century to meet our detective, the physicist James Clerk Maxwell. He was trying to put all the known laws of electricity and magnetism into one neat package, but he hit a snag. A big one. There was a contradiction, a puzzle in the math that just didn't add up.
The problem was with a rule called Ampere's law. Now, this law was rock solid for one thing. It said an electric current, electrons flowing in a wire, creates a magnetic field. Simple enough. But Maxwell thought about a capacitor. That's just two metal plates with a gap in between. When you charge it, a current flows in the wire up to the plate, but no electrons can jump across that empty gap. And yet, experiments showed there was still a magnetic field in the gap. How? If there's no current, there shouldn't be a magnetic field. It was a complete contradiction.
And this is where Maxwell had his stroke of genius. He said, what if it's not just moving charges that create a magnetic field? What if a changing electric field does the same thing? In that capacitor gap, as the charge builds up, the electric field is changing like crazy. Maxwell proposed this changing field creates its own sort of current, which he called a displacement current. It wasn't a flow of physical stuff, but in terms of creating a magnetic field, it acted exactly the same. This wasn't just a quick fix. This was the key that unlocked the whole universe.
So Maxwell's little fix did way more than just solve a weird capacitor problem. This leads us to our next section, the speed of light, because his solution was about to lead to one of the most mind-blowing revelations in all of science.
See, once he added his displacement current, his complete set of equations, what we now call Maxwell's equations, were just beautiful. They had this perfect symmetry. We already knew that a changing magnetic field makes an electric field. And now Maxwell had just shown that a changing electric field makes a magnetic field. You see it? They create each other. It's this endless feedback loop. He realized this dance could just keep going, creating a self-sustaining wave that could travel through empty space forever.
So the next logical question was, okay, if these waves exist, how fast do they go? Maxwell plugged the numbers into his equations, just basic constants from electricity and magnetism, and he calculated a speed. And the number that popped out was this: 3 × 10⁸ meters per second. An absolutely blistering speed, 300 million meters every single second. But was it just a number, a coincidence of the math?
No, not at all, because Maxwell knew that number. He recognized it instantly. This wasn't just any speed. This is the speed of light. In that single moment, the light bulb didn't just go on, it shattered. He realized that light itself, it is one of these electromagnetic waves. 3 entire branches of physics, electricity, magnetism, and optics, which everyone thought were separate, were suddenly, beautifully unified. They were all the same thing.
Okay, a prediction that big, saying light is just electricity and magnetism, that's got to be proven, right? So now we move from pure theory to actual technology. It was time to prove these waves existed, and, of course, figure out how to use them.
And it happened surprisingly fast. So Maxwell lays it all out in 1873. Just 14 years go by, and a guy named Heinrich Hertz actually does it. He builds a device that generates and detects these invisible waves, radio waves, right there in his lab. Proof. Then, hot on his heels, Guglielmo Marconi sees the potential. By 1895, he's not just making waves in a lab, he's sending them for miles. And just like that, the communications revolution was on.
So what Maxwell and Hertz had really done was show us that the light we see with our eyes, it's just one tiny color in a much, much bigger rainbow. This brings us to the invisible rainbow itself, a grand tour of the whole electromagnetic spectrum.
And here it is, the whole shebang. Everything from the long, lazy radio waves on one end to microwaves, infrared, all the way up to high-energy X-rays and gamma rays on the other. They are all fundamentally the exact same wave that Maxwell described. The only difference is their wavelength and frequency. And just look at that tiny little sliver in the middle marked visible light. That's it. That's all our eyes are built to detect. The rest of this massive, magnificent rainbow is completely invisible to us, but we figured out how to see with it anyway.
So let's just pick a few examples. You want radio waves? Just slosh some electrons back and forth in an antenna, and boom, you get these long waves perfect for radio and TV. Need something with a bit more energy, like microwaves? You use special tubes called magnetrons to generate them, and suddenly you have radar and can heat up your leftovers. Want to see inside a person? You need super high energy. So you slam electrons into a metal target, and out come these tiny, powerful X-rays. Different production, different application, but all of them are just different colors on that same invisible spectrum.
Let's really bring this home with an example pretty much all of us have in our kitchen, the microwave oven. Inside that box, there is a device generating waves that look exactly like the theoretical diagrams we've been looking at. So how does an invisible wave cook your lunch?
Well, the secret ingredient is frequency. The microwaves in your oven are tuned to a very specific frequency, 2.45 gigahertz. Now, why that number? Because it happens to be the resonant frequency for water molecules. Think of it like hitting just the right note to make a wine glass vibrate. Water is incredibly good at absorbing energy at that exact frequency, so the wave's energy gets dumped efficiently into the water molecules in your food, making them jiggle around like crazy. And jiggling molecules is just the scientific term for heat. It's a perfect, targeted use of one very specific color from our invisible rainbow.
So there you have it. We've gone from a tiny mathematical inconsistency to this grand cosmic theory, all the way to the box that reheats our coffee. This journey brings us to our final section, the wave-powered world. It just goes to show how one single brilliant idea can literally change everything.
All right, so let's just boil this whole thing down. The big takeaways. First, electricity and magnetism, they're not separate. They're two sides of the same coin. Second, a changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. That's the key. This back and forth dance creates a self-powering wave that just happens to travel at the speed of light. And that's because it is light, and also radio and X-rays and all the rest. It's all the same wave. And by figuring this out, by learning to see and use this invisible rainbow, we've literally built the modern, connected world.
And that really leaves us with one last, kind of awe-inspiring question. We've managed to master this entire invisible spectrum, building a global civilization on top of it, but before Maxwell, nobody knew it was even there. It makes you wonder, doesn't it? What other fundamental, invisible forces of nature are all around us, right now, just waiting for the next brilliant mind to spot a tiny little glitch in our understanding and unveil a whole new rainbow for humanity to explore?